This video is about slope fields. What is a slope field? A slope field allows us to obtain solutions graphically. So a lot of times we will find solutions analytically by taking derivatives or antiderivatives or something like that. But if something is not very easily anti-differentiated, we can use a slope field to then draw a graph of the solution. So that's something that is a benefit of slope fields. Slope fields are also easy to picture and visualize. So if we start to draw the picture of the of a function or of an equation on a slope field, it's pretty easy to follow the slope field, kind of like it's guiding our graph to see what it would look like. So we're just going to do a bunch of these, and by a bunch, I mean a whole bunch. So create a slope field for each differential equation. If dy dx is equal to x squared, we are having slopes of x squared at every point. So we would know that y is equal to 1/3 x cubed plus c. So that's something that we would know about this. So what does that mean? Well, if I do dy dx equals x squared, I'm going to draw little lines that represent the slope at any particular value of x comma y. So everywhere x is 0, y is 0. Or I'm sorry, dy dx is 0. So all of these would be horizontal. When x is 1 or -1, the slope is 1. When x is 2 or -2, the slope is 4. So notice that my slope gets a little steeper. And then at 3 or -3 for x, this would be 9, so it's even steeper because 3 squared is 9. So now, why does that help us? Because let's say I pick any point where this this function y equals whatever works out. So let's say I pick it here. Well, I can kind of see what the graph would look like just by tracing the slope field. And notice it looks like a 1/3 x cubed graph. Now, if this is where it is, it would follow something similar. So we end up with another 1/3 x cubed. I didn't draw that great, but if I draw this one, it would follow the path again. So all of these look like 1/3 x cubed graphs. Now, what about dy dx equals y? Well, all of my slopes would be dependent only on y here. So when y is 0, my slope is 0. When y is 1, my slope is 1. And when y is 2, my slope is 2. When y is -1, my slope is -1. And -2 slope is -2. Now, if I did a separation of variables here and dy over y equals dx, and then I integrated, I'd end up with the natural log of the absolute value of y is equal to x plus c. So what I would end up with is c, or some different constant, times e to the x. So depending on where my graph is, notice that I would have this asymptote at 0. And then let's say this point is picked as an initial condition. This would look like an exponential function. Now, if some point down here was picked, it would still look like an exponential function. It would just be an exponential function that had a negative value of c, which is why we have this absolute value of y showing up for natural log. So either one of those could work. Now, what about this one? Well, it's dependent on both x and y. So in that case, if x is 0, no matter what happens when x is 0, I have a horizontal slope. Except at 0, 0, I probably should have been a little more careful, because anywhere y is 0, I have a vertical slope, an undefined dy dx. At 0, 0, that just, you can't have 0 divided by 0. That is really nasty. So at 1, 1, and 2, 2, and -1, -1, and -2, -2, all of those would be slope of -1, just based on plugging stuff in. At these values that I'm drawing now, they would be +1. And as the graph kind of goes around, what's becoming apparent, I'm not going to draw all of these, but what's becoming apparent is this kind of looks like a circle, because all of these, no matter where I start, it seems like it's going to guide me along a path that kind of looks like a circle. So that's what would happen here. And if I anti-differentiated, notice I would have dy times y equals -x dx when I separate the variables. Then when I integrate, I get 1/2 y squared equals -1/2 x squared plus c. Then if I add over and multiply everything by 2, I get x squared plus y squared equals 2c, or just some different constant. That would end up being a circle. So sketch a slope field for each of the following. I'm going to leave those to you to do on your own, or else this video would take forever. There are many functions with the same derivative. Without some initial condition, you can't determine which path to follow, and we kind of talked about that up here. Unless I know the initial condition, I know that my path for this first one looks like a 1/3 x cubed, but where does it start? It could start anywhere along this path. So that's something we don't know. So that's kind of what slope fields are designed for. So I know that the graph of 1 looks something like this. So what I need to do is I need to find some sort of function or some sort of slope field where this would make sense. And that certainly looks like E, right? Because if I have this function, I could definitely mimic that on E. B looks like it would be able to mimic number 2, this line with slope of 1. Number 6 certainly looks like F could mimic that. And then D definitely looks like some sort of parabola situation. That's terrible. But some sort of parabola situation. Now, 3 and 5 confuse a lot of people. And so, because they both look trigonometric, because they are. So one thing that's kind of important to note is the graph of sine of x plus 4 has a slope of 1 at x equals 0. So that would match up with C. Whereas the slope of cosine at 0 is 0, and that would match up with A. And so if I just traced the graph, I could be able to kind of figure this out. Match the slope fields with differential equations. So this is a different problem. This problem is matching dy dx's. So that means we are actually looking for the slope fields instead of trying to find something that could possibly match these functions. So if I look at, for example, number 7, 1/2 x plus 1, that means that I need to find a graph that everywhere I plug in an x, I'm going to get 1/2 x plus 1. So what does that mean? That means that this one is solely dependent on x. So if I'm looking at this, I need to find something that is only entirely dependent on x. So, for example, if I look at A, this one is not dependent on X. This one is dependent on Y, because when Y changes, my graph changes. But if I look at, for example, letter D, notice that all of these, everything that has the exact same X value, has the exact same graph. And if I looked at it, if I plug in 2 or -2, I would get 0. If I plugged in 0, I would get 1 for a slope. And so that seems to be the case all over the place. So that one would be D. Number 8 matches with A, like we talked about. This one is only dependent on Y. And if you plugged in some slopes, you would see it. We already did 10 earlier. This one looks like a circle. So this one's B. And then that would mean that 9 matches with C, because if you look at this oblique asymptote here, what would happen is this matches everywhere X just so happens to be 1 greater than Y. Because if X is 1 greater than Y, then that slope would be 1. So that's kind of where that works out. Each of these, notice X is 1 greater, 3, 2. It would be 1 greater than Y. The slope would be 1 all throughout that line. So the calculator drawn slope field for this differential equation is shown in the figure. The solution curve through 0, 1 is also shown. Sketch the solution curve through 0, 2. So that would be this. Sketch the solution curve through 0, 1. That one would be this, or something similar to it. I probably drew it a little too narrow. It would probably be something like that. But what you notice is you see that these graphs can be completely dependent on where your initial condition is. So if I look at this and I do a quick dy over y equals x dx and do an integration really fast after a separation of variables, I have natural log of absolute value of y is equal to 1/2 x squared plus c. And then y is equal to e to the 1/2 x squared plus c. Notice what happens is if I take note of the fact that when I have an exponential function, I can rewrite this as a new constant in front. Notice that these can look very different. So what I have is I can have something where my function, if I have a constant that's negative in front, it would look like this. But if I have a constant that's positive in front, it would look something like this. So that's totally dependent on where the solution curve is. Calculator drawn slope field for this one is shown. Sketch the solution curve through the point 0, 1. That would look something like this, and then it levels off and goes somewhere like this toward the asymptote. Sketch the solution curve through -3, 0. This one would also go toward the asymptote and do something like this. Sketch slope fields for those. I'm going to leave those for you. One of the following slope fields is dy dx equals sine of x plus y, and the other is dy dx equals sine of x minus y. Where would you expect the slope to be 0 in the slope field for dy dx equals sine of x plus y? Well, if we know something about sine of 0 is equal to 0. So that would mean everywhere x plus y is equal to 0. So if I look for situations where x plus y equals 0, that would be at 0, 0. That would be at 1, -1, -1, 1, 2, -2. Those would all be situations where sine of x plus y is sine of 0. So if I'm looking at this, notice that when x and y are exact opposites, for example, -1, 1, -2, 2, this one should be sine of x plus y, just based on the way that we kind of think about this logically. When I look at this one, sine of x minus y, I would need x minus y equal to 0, which means that I need x equals y. So 0, 0, 1, 1, negative 1, negative 1, and so on. So that one would match up with this one, because all of these end up giving you 0.